Hi everyone, a warm welcome to all who are watching my PPT. This is M. Pavan from Data Science Group, Section B. I am here to explain you a topic called charge distribution and transport in polymers. Here we go to next slide to learn more about charge distribution and transport in polymers. Introduction. Polymeric semiconductors have attracted much attention because of their possible use as active materials in printed electronics. Thin film transistors (TFTs) are a convenient tool for studying charge transport physics in conjugated polymers. Means polymeric semiconductors have attracted much attention because of their possible active material in printing electronics. TFCs are the most convenient tool for charge transport physics in conjugated polymers. Two families of materials are reviewed here: fluorine copolymers and polythiophins. Because charge transport is highly anisotropic in molecular conductors, the electrical properties of conjugated polymers are strongly dependent on microstructure. Here, the polymers are divided into two types. Those are called fluorine copolymers and polythiophins. Because charge transport is highly isotropic in molecular conductors, the electrical properties of conjugated polymers are strongly dependent on microstructure. From here, we will move to next slide to learn more about our PPT, our topic. Molecular weight, polydensity, and regularity all affect morphology and charge transport in these materials. Charge transport models based on microstructure are instrumental in identifying the electrical bottlenecks in these materials. In these materials, we can easily identify electrical bottlenecks by using molecular weight, polydispersity, and regularity all affect morphology and charge transport in these materials. Polymeric semiconductors are a very promising and versatile materials family for flexible electronics. When properly designed, these materials dissolved in common organic solvents and can be proceeded from a liquid solution at room temperature. Such solutions are often called semiconducting inks because they can be disposed and patterned using low-cost technologies such as inkjet preview or set of painting. Means polysemiconductors are very promising and versatile materials for flexible electronics. With when properly designed, these materials dissolves in common organic solvents and can be proceeded from liquid solution at room temperature. Such solutions are often also called semiconducting inks because they can be deposited and patterned low cost technologies. Next, we move on to next slide to learn more. These are the structures of some of the polymers which we are discussing later. The first one is poly 9,9 dialkyl fluorine 2,7 diel co bethophenone. The formula general formula is R double bond C6H17. This was the structure of the polymer. And the second one is poly 9,9 di N octafluorine alt benzodiazole. The structure of this polymer is this one. The next one is poly 3-hexyl thiophene, and the structure is this one. And this next one is poly 5,5 bis 3 doctyl 2 thiol 2 comma 2 bithiophene, and the structure of this polymer is this one. And the last one is poly 2 comma 5 bis 3 alkyl thionine 2 ethyl thionine 3 comma 2 bithiophene. And the general formula of this polymer is R double bond CnH2n plus 1 CnH2n bond C double bond R CnH2n single bond C6H5. This was the structure of this last polymer. These are all our polymers which we are discussing. Experimental tools. TFTs as material characterization tools. TFCs based on classified as stagnant and coplanar top gate and bottom gate structures. The device behavior depends on the transistor geometry. And the next point is the electrostatic of a TFT indicate that charge transport occurs within a few nanometers of the semiconductor dielectric interface. It is thus not surprising that device performance depends strongly on the chemistry and roughness of that interface. Means the electrostatics of a TFC indicate that charge transport occurs within a few nanometers of the semiconductor or dielectric interface. It is thus not surprising that device performance depends on strongly on the chemistry and roughness of that interface. We will move on to next slide. This was the graph for TFC device structures. There are four types of structures in TFT device. First one is bottom gate stacked, second one is bottom gate coplanar, third one is bottom gate stacked, and fourth one is top gate coplanar. The active area of the transistor at the semiconductor dielectric interface is indicated. Now we can see these diagrams and we can easily find the TFT device structures. Now here the five colors are identified here. Source and drain contacts, gate dielectric, semiconductor, gate, electrode, active area of the channel. These are the five colors for the five structures. Next we will move on. Microstructure characterization technology. Typical microstructural length scales in polymeric semiconductors are of the order of a few tens of nanometers. Therefore, scanning probes instruments are most widely used to characterize polymer morphology. Next one, atomic force microscopic and electrostatic force microscopic has been used for this purpose. A few studies have used scanning tunneling microscopy (STM) to determine the electrical properties of polymeric monolayers. Means for the transport of polymerize the other part other programs in microstructural characterization techniques. The other techniques are atomic force microscopy (AFM) and microstatic force EFM has been used for this purpose also. A few studies have used scanning tunneling microscopy (STM) to determine the electrical properties of polymeric monolayers. The next slide is microstructural influence on charge transport in polymeric semiconductors. In conjugated polymers, the semiconducting properties come from extended pi orbitals through the conjugation of the unhybridized p-z carbon orbitals along the backbone. Means there are vast variety of polymers in our world. In conjugated polymers, the semiconducting properties come from extended pi bonds of the conjugation of the unhybridized p-z carbon orbitals along the backbone. Next point, the remaining polymeric semiconductors that are reviewed here can be divided into two broad families, as I like said before, fluorine copolymers and polythiophins. Both these polymer families have a relatively rigid backbone with attached alkyl chains for solubility and are able to crystallize. We will move on to next slide. Fluorine copolymers. Now we will first learn about the first part of polymers, fluorine copolymers. Fluorine copolymers has been extensively studied as active metal materials for LEDs and TVs 12, 14. There are relatively few studies on the use of this class of materials in field effect transistors 15 to 17. The most studied materials for TFTs are F8T2 and F8BT. The charge transport anisotropy observed in F8T2 is the result of one-dimensional order arising from chain alignment. Only has studied the effect of three-dimensional order by analyzing the effect of crystallization on charge transport in F8BT films used in N-type devices. Means the charge transport anisotropy observed in F8B2 is the result of one-dimensional order arising from chain alignment. In these fluorine copolymers, we are using a very vast number of examples for in which related to fluorine copolymers. In these widely used are LEDs and TVs 12 and 14. But the research on those are very less, and the most study materials are done on F8T2 and F8BT. We'll move to next. Polythiophins. The second part of the polymers, and which we said as two families, and the second family of those polymers is polythiophins. Polythiophins are a heavily investigated polymeric semiconductor family because of their high mobility up to 0.6 centimeters square per versus and commercial availability. Unlike fluorine copolymers, polythiophins have a strong tendency to self-assemble into crystal crystallites when cast into thin films. Means in apart from the fluorine polymers, the polythiophins have the capability of self-assemble into crystals or thin sheets or thin films. Next, well, thermal analysis usually increases their degree of crystallinity. Crystals are often detected in spin coated films of these materials prior to thermal treatment. Means in well, thermal analysis usually increases their degree of crystallinity. Crystals are often detected in spin coated films of these materials prior to thermal treatment. Next, we move on to next slide to learn more about polythiophins. Here we had a graph of EFM measurement of the potential profile. EFM measurement of the potential profile in a conducting polythiophene monolayer deposited between two electrodes, reprinted with permission from 37 2001 VCH. Means we can find that in graph on x-axis we take surface distance in μm, in potential in y-axis we take as potential V. When we observe the graph, we can easily say that the graph is decreasing from right to left, and and the values are from 1, 2, 3, 4, 5, 6, and the graph is gradually decreasing from here to there. On y-axis, potential was decreasing and surface distance was increasing. Then we will move on to further slides to learn more. Effect of crystalline structure on charge transport. The characterization between charge transport and crystalline structure in a TFT was first demonstrated by Sergius in The late 22, the mobility of P3HT films containing mostly planar oriented crystals is 3 orders of magnitude other than that of films containing mostly hexagon structured crystals. Kim ETAL 38 was have found evidence that P3HT regularity in the 90 to 97 percentage range affects the overall crystallinity of the film but has little effect on structure which is mostly edge on. Next we will move on to next slide. Linking morphology and electrical properties charge transport models. The morphology and microstructure of polymeric semiconductors and of semi-crystallic polymers in particular play a very important role in charge transport in these materials. Means the morphology and microstructure of polymeric semiconductors and of semi-crystalline polymers in particular in means in one particular way play a very important role in charge transport. Means these are the terms and these are the ways in which they play with great role in transporting charge in polymers. Next, the ME model has been successfully applied to PQT12 to show how different microstructures affect carrier mobility by altering the energy gap trap distribution. Next, we will move on. Here we came for conclusion. In this, the increase in electrical performance of polymeric semiconductors over the last 10 years has been remarkable. Nevertheless, in addition to displaying sufficient charge transport properties, polymeric semiconductors will have no become will have to become reliable, robust, and reproducible, in short, predictable, in order to be used in commercial products. Our understanding of these materials is still incomplete despite a considerable amount of research over the past 20 years. Seemingly well established results are constantly changed by new experiments. Means our research and experiment is still ongoing and we still research further. The what we defined earlier will be changed and also changing nowadays, so our research should not stop and our research on the past 20 years will be changed or will be changed further, and exact values of what we are need will get by further experiments and researches. And okay, then we will move on. Then thank you for giving me this golden opportunity to share my knowledge with you and some few words about my topic. Thank you for giving me this golden opportunity. Thank you all.